Morning,
Morning, Doctor.
everybody in the class. Okay, so we are doing revision on the test, which will be held tomorrow. I didn't realize that today is holiday. So sorry. Cuti hari ni rupanya.
I don't realize as well.
Jarang-jarang. Birthday. Right, okay. So shall we discuss this one? I share with you just now. Last session test, which during PKP, okay. Do you have this copy?
Yes,
Yes, Doctor.
Okay, Telpen, can you read question number 1, please?
Okay, Doctor. The unity feedback system is shown in figure 1. GS equals K bracket S square minus 4S plus 8 over bracket S plus 4 bracket S plus 10. From the given open loop transfer function, GS, determine the following. 1. The imaginary crossing of the root locus of the closed loop transfer system function, hence the gain at the crossing. 2. The arrival angle of the root locus of the closed loop transfer function. 3. The breakaway point of the root locus of the closed loop transfer function is given as S equals to negative 6.05, hence determine the gain at that point. 4. Using the information gathered from 1 to 3, sketch the root locus of the closed loop transfer function. And 5, hence determine the range of gain of K for the underdamped stable system and the critically damped system.
Okay. Thank you very much. Okay, how to tackle this question? Have you tried? Have you tried the question?
No, so this is the first time seeing the question.
Oh, first time. Oh, yeah. Oh, the one that I give it to you. We have two tests, two type of tests. One is the real one. The other one is for those who are not able to come due to sickness, due to internet problem, rural area during MCO. Okay. So this one is the real one. The one that I gave previously, the old one is the repeat one. So we're going to find the imaginary axis, imaginary crossing of the root locus of the closed loop transfer function. Okay. So we have to find the closed loop first, isn't it? Given. Okay, okay, so given open loop transfer function, which is GS, okay. So now we have to find the closed loop, G closed loop. Okay, so G closed loop will be k s square minus 4s plus 8. Okay. S plus 4, S plus 10, plus K S square 4S plus 8. Okay. So now the denominator of closed loop transfer function above is the characteristic equation. Okay, which is this one. Okay, so S plus 4, S plus 10, S square minus 4S plus 8 equal to 0. Okay, so that is the characteristic equation. Then we simplified. So it will become what? Can you simplify it? K plus 1 S square plus 14 minus 4K plus 8K plus 40 equal to 0. Okay. This is so far okay? Understand?
Yes, Doctor.
Yes. That's
Okay.
the Ruth-Hurwitz.
Yeah, you have to simplify this one. Okay. Then they become here. And from there, you can insert Ruth-Hurwitz table. Okay. So your Ruth-Hurwitz table will be S square, S power of 1, which is K plus 1, this part. At K plus 40. Okay. 14 minus 4K, 0. Then okay. So after you fill up, is after you plug in to the Ruth table. So now you have to fill up the S power of 0. Okay. So if you fill up, there is a case of ROZ over there. So LK plus 40, which is 0. So S1 is a row of 0 special case. Okay, so we'll give you K is equal to 14 divided by 4. K is equal to 3.1. Okay. Then go to S square row. Okay. So you will get a 3.5 plus 1. Insert the gain value plus 8. 3.5 plus 40. Okay. Go to 0. Okay, so you will get the S value at plus minus J 3.84. Okay, 3.84.
Doctor, could you go to the previous slide? I missed the part.
This one. At S power of 1, we have a row of zeros. So we have to, use the row of zeros technique to gain the gain K 14 divided by 4, which is 3.5. Okay. Then you use the gain, you insert inside the S square, the equations auxiliary polynomials, S square. Then you will get S at plus minus j 3.84. Next question is the arrival angle of the root locus of the closed loop transfer functions. So this one, the k is 3.5, right? At this point, and cross the imaginary axis. For example, I don't know the locus. The root locus is not given. Okay, so in this case, the root locus is not given. So if you want to see the root locus, you have to imagine. Otherwise, you have to use Matlab. So for the purpose of revision, let's go to the Matlab online. Okay. We go to.
Do we use Matlab during the tests? No, right?
That's a good question, actually.
I mean, we can see our screens, so you can see our open Matlab.
You have used the 2 device, can? You use 2 device, so everybody will see you. So no need Matlab online, just for the revision purpose. Okay, okay. So you can register Matlab online. Have you did this? You register Matlab online. Okay.
Oh.
So I share with you. This lesson where you can register first using your name, okay, and your university and your affiliations as a student. I already registered, okay, but this license valid only for 1 month. So after 30 days, you have to renew again if you want to use it again. So I'm going to plot these questions, the root locus for this, if I can. Okay, I try. I don't know they have the function or not. TF. Okay, G. So assume K equal to 1, okay? So we start to insert S square minus 4S plus 8. Okay. Divided by S plus 4 multiply S plus 10. Okay. Oops, what's wrong? Oh. So you have to put multiply here because the computer don't understand. Okay. There you go. And then R locus G. Do you see what I typed here? Can you see?
Yes.
Yes, also.
Yes, doctor.
Can you see the figure?
Yes.
So you have 2 complex conjugate zeros on the right hand side of the S-plane, and you have 2 real poles on the left hand side, okay, which is this one, okay, this one, and this one, okay, okay. So the position, the cross, the root locus cross intersection with the imaginary axis is over here. There you go, 3.54. Our answer is 3.84. Our answer is 3.5 again, and the poles is at 3.88 minus plus minus j 3.88. We obtain 3.84. The problem with this online, you cannot scan. I tried to drag the point. No, it didn't work. Okay. Boleh, boleh punya. Tadi semalam tak boleh. So 3.84 is about here. 89. 84, 89, somewhere here lah. Okay. Can you see? More Jun, can you see?
Yes.
Sadana Sakit, can you see?
Yes. No.
Okay, right. So now we go to the second question, which is the arrival angle of the root locus of the closed loop transfer functions. Okay. This one is part 2. Locus of the closed loop transfer function. Okay. So what is the formula to find the arrival angle?
The sum of all poles.
Sum of angle of zeros minus sum of angle of poles. Okay. So that is the formula.
Terbalik kan, Doctor?
Got it?
That one is departure.
Arrival.
Okay, I think arrival is poles minus zeros.
Okay, sorry about that.
And then, don't we also have to add 180 degrees or something? I can't remember.
That is the formula.
That's
Right.
the formula. Okay, correct me if I'm wrong. Okay, so we draw so that we can see. Okay, so the poles first, the zeros first, minus 4, 10. Yang ini adalah positif 2, J2 minus J2. Okay. So kita nak tengok dia punya arrival angle kan. So arrival angle should be correspond to here. Okay. So the arrival angle theta A is equal to theta 1 plus theta 2 minus theta 3 plus 180 degrees. So theta 1 is over here. Theta 2. Then theta 3. Okay. Okay. So theta 3 is 90 degrees kan. So therefore theta A. So how are you going to find theta A? Theta 1, theta 2?
Arctangent.
Tanyalah Noraina, Safika. Lama tak tanya ni.
Yeah, Doctor.
How you find theta 1?
Theta 1
Is
arctangent
arctangent
2 over 12.
2 over 12. Very good. And the answer is?
Sekejap. Answer is 9.46.
9.5 lah. Theta 2. Sekali lagi. Aina?
Theta 2 arctangent 2
2
over 6.
over 6. Good. Which is
18.4.
18.4. Thank you very much. Theta 3,
Theta 3, 90.
90 degrees. Sudah tepat. Your variable there is 117.9. Okay. So the breakaway point. So far only 15 students joins. Yang lain tak tahu dah tidur agaknya.
Doctor, can we get back to the angle? I wanna
Minum
confirm
kopi.
something.
Okay, sorry.
No. I wanna ask. What's the reference?
Huh?
Well, what's the reference point is at 2J?
Ini. Sini.
Yeah. Why is it there?
Okay. Breakaway point? Huh? Sorry.
I mean, why do you choose that as the reference point for the angle? For rival angle.
Usually we choose the positive side instead of the negative side. The positive J2 instead of minus J2. It's the complex conjugate zeros. Okay. So when you say zeros, is correspond to the rival. When you say poles, it will correspond to the departure. Kan?
Yeah. Oh,
So you ambil yang positive side lah.
gotcha. Thank you.
Breakaway point. So if we see the plot, okay, mana plot tadi? Breakaway point. Abdul Rahman, Syarudin. Man.
Betul.
Breakaway kat mana, Man?
Daripada post pergi ke zero tu, kat tengah-tengah.
Between two poles ni lah.
Okay,
kita tengok komputer. Berapa, Man?
Negative 6.05, negative 0.08 imaginary.
Alah. Breakaway point mesti real, tak ada imaginary.
Oh.
Boleh lah tu, minus 6
Okay.
Minus 6. Minus 6. Tu daripada komputer. Manual. So manual is kita pakai formula lah. Kan? Formula. Jadi kalau kita lihat di sini the breakaway point of the root locus of the closed loop transfer functions. Kan minus 6 kan? Dia bagi ke tak? The question. Given S equal to minus 6.05. So you have to calculate the gain. There is one question. I don't know. Maybe Arab brothers. He asked about in the WhatsApp. The gain of K at the dominant poles. Okay. So the way you calculate the gain is similar like this. Okay, which is K equal to the open loop transfer function.
Okay, you're not showing the screen.
Oh, sorry. I'm sorry. It's not automatic. Somebody has to create it automatic. When I pull the Apple Pencil, yeah, terus.
Good business idea.
Kau buat lah ni. FYP.
Yeah, for capstone doctor.
My old iMac is broke last week, so I buy a new one. Okay, for the purpose of the class. So S is equal to minus 6.05. Okay, so you replace S inside here. Okay, 0.1177, 0.1177. Okay, to Brother Amir who asked in the WhatsApp group how to calculate the gain of the dominant pole. You just take the dominant pole value and you insert inside the transfer functions, which is I shown here. It depends. Sorry.
Doctor, regarding this, right? I understand this. We do this because of property, but why do we use the open loop transfer function and not the closed loop transfer function?
Because all the gain is based on the open loop transfer functions.
Okay.
It's based on the magnitude criterion. Magnitude
Okay,
criterion. Temple.
All right. Thank you, doctor.
So the numerator one is correspond to the poles. This one is the poles. And this one is the zeros. Kita balik. Okay. Kalau dalam gain calculations. Then number 4, question number 4, using the information gathered from 1 until 3, sketch the root locus of the closed loop transfer function. So sketch. Okay. So you have the you have the -4, -10. This one is 2, J2, minus J2. Okay. And then based on calculation number 1, which is number 1, 3.84. 3.84 is somewhere here. Okay. And then what else? Oh, the breakaway point, -6. Okay. What else? Departure angle. Okay. Theta A. 117. So you can draw the root locus. Okay, one is here. Okay, green one is here. Okay, start from the poles, ended at zeros. And then one will go up. Okay, and the other one will go to this side. Okay, roughly lah, yeah. Okay, so this one considered as acceptable freehand draw for the root locus sketching. Hence, determine the range of gain K for the underdamped stable system and the critically damped system. What do you understand by that?
Damping ratio.
By that?
I get the root.
Okay. Kalau here, range of K for underdamped system is 0.118. That is from the breakaway point through the K through the 3.5. 3.5 is the reading of the this one here. K 3.5, and here the K is 0.118. 1177. So 0.118. Okay. So that is the considered as the region of the underdam. Okay. So if you want to know region of underdam is SI using my gray color. Okay. So this is underdam region. Okay. Okay. Nurliana Izati. So when is the critical? Critical is critical dam.
3.5.
Critical dam when K is equal to 0.11. This one, K is between 0.118 and 3.5, not equal to 0.118, not equal to 3.5. Okay. Understand?
Can you repeat that, Doctor?
Sorry?
Can you, I don't understand.
Don't understand. Which one?
That last statement you said.
Critical dam though. Critical dam ni when K is equal to 0.118. In this case, in this equation, 0.118 is not included because this is under dam region. But when K is equal, okay, bukan less, is equal 0.118, so the system is critical dam.
And how about 3.5?
3.5 is where the stability of the system is critical.
So kalau K equals to
Yes, stability and stability, critical stable and critical dam is two different things.
Oh,
It's two different issue.
then
Most of the students assume critical dam and critical stable is the same. Actually, it's not. It's not. It's not at all. So I'm going to ask you, what is the key value to make the system marginal stable or critical stable? Ho Jeng Han.
3.5.
Yes, K equal to 3.5. That will make the system critical stable, not critical damping. Most of the students assume critical damping and critical stability is the same, but actually it's wrong. Okay, you get it?
thank you, Doctor. Glad I asked.
Okay, faham tak?
Yes, faham.
Okay, that's why you must have a revision. Otherwise, you are in the, traveling in the moon, in space. Okay, finish, Telpel. Question 1, finish,
All right,
Finish,
I believe so. Let me just go through the set. Yep.
Okay, Telpel, question number 2, please.
Number
Our
2.
newsreader.
A closed loop unity feedback system as in figure Q 2.1 has a root locus as shown in figure Q 2.2. Design a PD controller to yield a damping ratio of 0.59 with a threefold reduction in the system's settling time. For the compensated system, determine the peak time and the steady state error. And lastly, sketch the step response to the compensated system.
All right, thank you very much. Okay, now in this question number 2, okay, everybody please focus. The open loop transfer function is not given. Am I right? Open loop transfer function is not given.
Yes.
Betul? Azira?
Ya, betul.
Ya, betul. And the plot is given. Am I right? Azira?
Yes, doctor.
Compared to the previous question, question 1, open loop is given. Am I right? Open loop transfer function is given. Azira?
Yes, doctor.
And then the plot is not given. Correct? So you must adapt the situation where the plot is given, transfer function is not given. Or transfer function is given, plot is not given. Okay? So now you are required to design the PD controller based on the question. Open loop is not given. Okay, but there is the plot of the root locus is given on the figure Q2. Okay, and then damping ratio is 0.59 with a threefold reduction. What do you mean by threefold reductions?
By 3.
Divide by
3.
divide by 3. The settling time divide by 3. Kalau settling time-nya before controller design is 9 seconds, so the new settling time will be
3 seconds.
9 divided by 3, which is 3 seconds lah. Okay, meaning that the system will settle faster compared to the old one. The new one will settle at after 3 seconds after PD controller, and the old one will settle after 9 seconds without PD controller. You understand tak apa yang cakap ni?
Yes.
Kena berasap. Belum berasap lagi
Yes.
Okay. So what is the open loop transfer function?
Isn't it the same as the, because they said it's based on the root locus in figure Q point.
Okay.
It's in same with figure Q.21.
Okay, we observe the plot. We observe the plot. Okay, so a very nice graph using Excel. Right. So you have how many poles there?
3.
3, eh? Any zeros?
No.
No zeros. Okay, so it will be K over. So what is the first pole value?
-1 point something.
Can you see using your magnifying glass? If any, Ali Imran, what is the first pole? The first pole value in figure Q2. Zoom in. Zoom in or zoom out?
Around 2.
Zoom in lah. So kalau tengok graph tu, 1 centimeter equal to 2. So it should be 1. Am I right?
Yeah, I think it's 1.
1, eh? Second poles?
I think it's 3.
3.
-3.
Yeah.
Oh.
And the third pole, -12. Okay, so the way you write it is like this. From the root locus plot, 3 poles observed, -1, -3, -12. Okay, so we will get K, S plus 1, S plus 3, and S plus 12. Okay, so that is the open loop transfer function. Okay, so given zeta 0.59, we know that cos theta is equal to zeta. So theta is equal to inverse cos 0.59, which will give you theta how much?
53.84.
53.8 degrees. Correct. Thank you very much. Okay. Okay, so tangent 53.8 degrees, which is equal to 8 divided by x. Okay. 8 divided by x. X is unknown. Okay. X is unknown, which is will give you the dominance, which is X tu berapa? What is the value of X? What is the value of X?
Five point eight.
Huh? Berapa?
5.86.
5.8. So I'm using my mouse. Okay. So the 53.8 is somewhere. Let's say this is my freehand drawing. Forgive me if it's like error. Okay. So if this is the 53.8 degrees, right? And our concern is here. Okay. Our concern is here. So you have what do you call that? You have to draw, you have to print this rule locus, and you have to use a ruler. Okay, otherwise you cannot find the answer. Okay, so in this case, okay, so this is 53.8 degrees. Okay, this is 8 and this is X, correct? Berapa X tadi? Nina? X berapa?
5.86.
5.86. Okay, in order to achieve this, what do you call that? SD. Okay, so what is the crossing point there? What is the crossing point? SD. Anybody? Using your pen, iPad, Neuma? What is the
How did you
intersection?
get 8? I don't
Huh?
I don't understand how did you get 8? For the tangent 53.8 equals 8 over x, right? How did you get 8?
8, you get 8 when you draw the 53.8 zeta damping ratio.
Okay, so we only once we draw, then we will get, okay.
First, the zeta is given, okay?
Yeah.
Zeta is given 0.59. Then we get the theta. Theta is the angle between the damping ratio line and the root locus line. So you have to print this one and draw using a ruler.
Noted,
And what
doctor.
about the x, doctor?
Huh?
What's the x? What's this?
Forget about the x first.
Oh, okay.
Find the SD, the cross line, then, the intersections.
In coordinates, it's
Yeah. Forget
1.8.
Forget about it. It's confusing. Okay.
Based on my iPad, it's 1.8 plus
Berapa?
J 2.
Minus 1.8.
Not 1.8, 1.5.
1.5 minus 1.8 and J 2.2. Okay. So we follow the answer schema lah. Okay. So this is this one. Okay. Correct. Okay. So now you have the SD, the dominant poles, minus 1.8 plus J 2.2. So the real part is minus 1.8.
Doctor, you're writing something? You can't see the screen.
Oh, sorry. Imaginary part is 2.2. Okay. So settling time is 4 divided by real, which is 4 divided by 1.8, which is 2.22 seconds. Okay. So the settling mu is 2.22 divided by 3. That is the meaning of threefold reductions. Okay. So will be 0.74 seconds. And that will make the real part, the real new part will be 4 divided by 0.74, which is 5.4. Okay. And then the omega n nu will be 5.4 divided by 0.59, which is 9.15 radian per second. And then the imaginary nu will be omega n nu. Okay. 1 minus zeta square. So the new value is 9.15. 1 minus 0.59 square. J 7.39. Okay. So the new dominant pole is S D nu by 4 plus J 7.39. Okay. Then we plot it. Okay. Then we mark the pole. Okay. And the new dominant pole, which is here. Okay. Then every pole correspond to the new dominant pole. Okay. And then since we are going to design for PD, so we put PD anywhere. Okay. Assume is here. Okay. So this one will be the what do you call that, zeros. Okay. Okay. For the PD controller. Then we put the angle theta 1, theta 2, theta 3. Okay. And for the zeros, let's say put it as theta z. Okay. All right. Then theta z is equal to theta 1 plus theta 2 plus theta 3, 180 degrees. So theta 1 is using a arctangent 48.2 degrees plus 108 degrees plus 120.8 degrees. Okay. So you will get theta z is roughly about 97. Okay. 97 degrees. Okay, so let's say this one is A value unknown. This is minus 5.4. And this one is 7.39. Okay. So tangent 180 degrees minus 97. 7.39 5.4 minus A, the value. Then 8.1, 5.4. So A will be 4.49. Therefore, S plus 4.49. The PD controller. Part 1. Is it okay?
Yes, doctor.
Okay. Number 2 is for the compensated system. Find the peak time and steady state error. Okay. So P new, okay, is pi divided by imaginary.
7.39.
Yeah,
0.425.
11.39, 0.43 seconds. Okay. And using final value theorem. Okay. So K is equal to S plus 1, S plus 3, S plus 12, S plus 4.49. Okay. At the dominant pole's value. Okay. What is the dominant pole's value just now? Okay, you find it. Okay. So it will be 88.9. And KP, the proportional controller, will be limit S to 0, 88.9, S plus 4.49, S plus 1, S plus 3, S plus 12, 110.9 KP, because this system is type 0, okay, no poles at the origin. So ESS will be 1 over 1 plus KP, which is 0.009 or 0.01, the steady state error. Then sketch the response. Okay, so this is just the icing of the cake. Okay. Something like that. Okay. So can put the TP here. TP is 0.43. Then the settling time. Settling time will be the one that 3-fold reductions. 0.74 seconds. Okay. Then the error 0.01. So meaning that the input will be just like that, 1.0. Okay. So the error state, okay, the ESS 0.01. So how you want to overcome the error 0.01? Become 0.
We have to use a PI controller, right?
I
Because only then we will.
Yeah. use a PI controller, so the ESS from 0.01 will become 0.
Doctor, just want to clarify something. We use the ESS equation of 1/1 plus KP because this is type 0, right?
Yes, type 0, 1/1 plus KP. So you have to find the KP using the limit value.
And if it's type 1, is 1/KB, right?
1/KB, definitely. And if KA is ESS 1/K.
Thank you, Doctor.
Okay, ni Umar. Baca soalan nombor 3. Question 3.
Sure. A unity feedback system represented by figure 3.1 has an open loop transfer function as that s plus 2 with a pole s bracket s plus 5, s plus 10, and s plus 20. So the frequency response of GS and KGS is given in figure Q3.2a and Q3.2b. KGS is the plot of the system when gain K is applied. Given KGS is the upper plot and GS is the bottom plot as labeled. Question 1, determine the stability of GS by examining the system's gain margin and phase margin. Question 2, hence identify the phase margin frequency and gain margin frequency. And question 3, using the magnitude plot of KGS, identify the new gain applied. Hence, from the plot, determine the range of K, the system to be stable.
Dah.
Yes.
Okay, macam inilah. The question for tomorrow is something like this. Okay. From chapter 1, chapter 2, and a little bit chapter 3. Okay, the plot is given. Okay. The plot is given. Okay. So we have two what do you call that? Magnitude plot tu ada dua. Why? Azira?
Before and after?
Before and after? Before what? Before lunch and after lunch?
Ada magnitude dengan phase.
Huh?
I don't know.
Apa dia nak? Determine the stability of GS by examining the system gain margin and phase margin. Okay. Right. Okay. Oh, I see. Okay, okay. K itu is when you have a gain adjustment. KGS. The dotted line tu after gain adjustment. Yang solid line GS tu is without gain adjustment. Faham? Azira?
Faham.
Huh?
Okay.
Cuba ulang balik. Repeat again what I said.
Yang dotted tu after gain adjustment. The solid line is before the gain adjustment.
Maknanya normal lah.
Yes.
Normal open loop. Okay, so we want to find the from the open loop, we can obtain 5 information. Okay, 5 important information, which is the gain margin, which correspond to the omega GM, gain crossover frequency, and then a phase margin, which correspond to the phase crossover frequency, and then system stability, status stable or not stable or critical stable. So 5 info: omega gain margin GM, omega GM, phase margin PM, omega PM, and then the system stability. So since this question is direct, okay, Aina, Noraina,
Yeah, doctor.
can you find me the value of gain margin? From how we going to find the gain margin from this plot?
Tak tahu lah, doktor.
Astaghfirullahaladzim, tak tahu. Tengok dekat phase curve minus 180 darjah. Berapa frekuensi ni? What is the frequency ya?
Oh,
Nampak tak? Pakai magnifying glass. Dia pakai spek tak? Pakai spek kan?
19.
19? No lah, telpon. Mana ada 19? Log scale tu.
That
10.
wasn't me,
Oh,
That wasn't me. That was Satnam.
estimate lah, estimate. This is 10, okay. This is 20, am I right? Di log scale tu.
Yes, doctor. So it's 19 or 18.
Kan 19 ke 18, 18.5.
18 lah, no point lah. 18
Okay,
lah
18.
Ho. Mana ho?
Yeah, that's
Ho.
me.
Are you
Yes.
there?
Yeah, I'm here.
You agree with me?
Yeah, 18 lah.
Sepak dB. 18 dB.
80 dB, yeah, minus 80 dB, yeah. If we go
18,
up and look at
18
the plot, yeah.
Okay, 18 goes here.
80 bukan.
No lah.
Oh no, 18 radian per
ah.
second, but the gain margin is 80 dB.
Wait 18 radian per second. Okay.
Yes.
Okay, Aina, berapa gain value at 18?
80
Minus 80
minus 80.
Jadi dia punya margin dia here, the margin. This one we call it as a gain margin. Gain margin. Aina, faham tak?
Faham, doktor?
Minus 80. So it will be 80 decibels.
80.
Okay. Ini kita panggil dia omega GM. Gain crossover frequency. Sama. Ini pun sama. Omega GM. Okay. Understand?
Understand, doctor?
Imran, understand?
Yeah,
Imran tidur,
okay. Understand.
Ali Imran? Okay, phase margin. Phase margin occurred when the gain curve cross at 0 dB. Where is it?
0.002.
Here. This is 0.01 kan? This is 0.01. Dia dekat sini. Sini. Sini ya Telpon. 0 point.
Doctor, Sadnan is speaking, not me, doctor.
Who?
Sadnan is speaking just now. Voice maybe a bit
same voice. Same signal. Okay. Omega PM. Phase margin. Sadnan.
Yes, doctor.
0.002. Okay, don't know about. Okay, then goes here. 0.02 is here, somewhere here. Okay.
Negative 90.
Wait, this is omega PM 0.002 radian per second. Okay, so there is a gap between here minus 180 and here. So what is the value of phase here? estimate
Negative
minus
90.
90.
minus 90 lah, more or less lah. Okay, so the phase margin is equal to minus 90 minus 180 is equal to plus 90 degrees. So what is the conclusion? Stable or not stable or critical? Azira?
Stable.
Stable. Azira, omega GM berapa? What is the value of omega GM?
Omega GM. 18, right?
Omega GM, gain crossover frequency, berapa? Tadi dia cakap
18 radian per second.
18 radian per second. What is the value of omega PM? Phase crossover frequency?
Omega PM 0.02 radian.
0.00?
0.02.
No, 0.00.
0.0002
radian per second. Okay. So that is the concept of gain margin and phase margin. Good. Hence, identify the phase margin frequency and gain margin frequency. Okay, solved already, 1 and 2. Number 3, using the magnitude of plot KGS, identify the new gain apply from the plot. Okay, tengok plot tu. Okay, I clearkan everything once. Where is my eraser? Nurliana? Nurliana? Nurliana tak ada. Imran Shamsul? Imran Shamsul?
Yes, Doctor.
So this is the ES, kan? And this one is KGS. So berapa banyak ni? Dia lift up ni, berapa dB from the graph?
Kira 30 dB.
Kira ni dulu. Satu kira ni. Berapa?
40.
Dulu. Banyak sangat tu. 34. Jawapannya 34. 34 decibels lift up. Okay. So lift up 24 decibels. So what is the K value? So how to calculate it? 20 log K equal to 34. So K is equal to telpel antilog.
Doctor, calculating.
Antilog. 10.
10 over 34 over 20.
Berapa? How much?
50.19.
50.19.
0.19.
50.19.
Yes.
Okay, so the range of stability is K equal to 50. Okay. All right, finish this part. You want some more? You want some more?
Sure, doctor.
Okay.
Excuse me, doctor.
Yeah.
So for the test, we study till here to till the phase margin and gain margin.
Yeah, you have to. They will give you the plot, then you have to access the value from the given question paper.
Yeah, but I mean for chapter 3, we study till this part, right?
Until stability and steady state error.
Oh, okay.
Steady state error.
Okay, thank you.
Huh? Okay.
Doctor, you said the questions are quite similar in nature to this past year,
The
right?
format lah. The format is about.
Except we have 2 questions, not 3, right?
2 questions. Yeah. 2 questions which will be you will download twice. Sorry, you will unload once. Q1 and Q2. You answer Q1 first. After finish Q1, then you upload to the e-learning. Then you answer Q2. Then after you answer Q2, finish the test, you upload the question 2.
We really gotta print.
Better print. If you have a printer, you better print the questions. Because
I mean,
you will use the root locus plot and the boot plot.
I personally don't mind printing, but there are a lot of students who don't have printers at home, so that's gonna
Those
be.
who don't have printers, they have to use the laptop and the handphone to measure.
Oh my God, that's gonna be hard.
But as the lecturer, after 31 years working, we have a wisdom. I didn't get that. Could you try again? Sorry. We have a wisdom how to tackle these issues. Okay, for those who are incapable. So as long as the answer is in the range of acceptable region, it should be okay. I'm okay with it. Okay. Let's say you measure the lift up. The answer is 34 decibel. Ali Imran measure 30 decibel. Telpel measure about 38 or 40 decibel. I accept that. I accept that answer. Both answer I accept. As long as the answer is not 340 decibel. I didn't catch that. Could you try again?
Your phone is trying to have a conversation with you.
No, not my watch.
Oh, your watch.
I'm sorry about that.
No worries, doctor.
Okay, so can we go to the second questions, the second set? Boleh tak?
Can, doctor.
No break. Can or not?
Problem.
Just relax now, listen, okay? Okay, I download the second questions, which is I think we discussed already this one, isn't it? Telpel, can you check whether I discussed already this one? Where is it? No. This one.
Doctor, actually, I have another question, right? Regarding, because you sent the front cover, the plagiarism form, right? And you said to consolidate that with our answer script. Are we supposed to do it for both the answer scripts or just the
only
first
one? Only one. The Q1. Either one will do. Right. As long as you save the file using your name, as I shown in the WhatsApp. For example, Azira Ahmad Q1.pdf. Azira Ahmad Q2.pdf. Azira, faham tak? I'm saying to you. Azira?
Yes.
Do you understand?
Yes. I need to put my name and point question
as the file name of your answer script. Yeah. Azira Ahmad Q1.pdf. Azira Ahmad Q2.pdf. Any Arab brothers here? Any Arab brothers here?
Yes, doctor.
Who? Name?
Muhammad Khalid.
Khalid. Okay, tell your Arab brothers, man. Okay, Khalid, for tomorrow, you have to answer Q1 first. It's a password, one password. Then submit. Submit as mkhalid q1.pdf. Submit to the e-learning. Then you open Q2 with the new password. Then after finish, you save as mkhalid q2.pdf. Do you understand, Khalid?
Yes, Doctor.
Can you tell your other brothers, friend, like that?
Yeah, sure.
Don't put other names that not related to you. For example, Q1, test, whatever. Your name is important because from there, I will trace your answer script. So
Okay.
our class have about 45 students. So if everybody answer 2 questions, 2 multiplied by 45, you have a 90 files in the e-learning system.
Yeah.
So please assist your lecturer by putting your name, telpelgil q1.pdf, telpelgil q2.pdf. Okay?
Okay, Doctor.
Okay. Okay, this one. Telpel, did we discuss this one last time?
I don't remember doing so, but I could be mistaken.
No, I think no. Nick, Umar, did we discuss this one last time?
I don't believe so, Doctor.
Huh?
Not this particular file. No.
Okay. Kalau no, Azira tolong baca. Azira Ahmad tolong baca.
A unity feedback system is shown in figure Q1.1. The root locus of this system is depicted in figure Q1.2.
Okay.
A, from the root locus in figure Q1, determine the following. One, the forward transfer function GS, 2, the asymptote point and the asymptote angle, 3, the angle of departure or arrival for the system. B, if the system is operated at 10% of overshoot, identify the following. 1, the dominant closed loop pole for this case. 2, the operational gain K at this point. Verify the validity of the second order approximation. And 4, for a step input response, determine the setting time, the peak time and the steady state error.
Yeah. Finished?
Yes.
Okay, thank you, Azira. Okay, so now open loop transfer function is not given, just a block diagram, but the real plot scale is given. Okay, so how are we going to do?
Get the poles and zeros.
Okay.
I think it's S plus 3.
Okay. So question 1, from the locus plot given. Okay. GS equal to
S plus 3 over S plus 4.
So you have you have 1 zeros, 1 0 and 3 poles. Okay. The first pole is the real pole, the second and the third pole is the complex conjugate. So it will be K S plus 3, okay, S plus 4, S plus 2 plus J1, S plus, sorry, minus. Okay, betul lah. Minus J1, okay, correct?
Doctor, one question. Since this is just a forward transfer function, because it
forward.
hasn't been combined with K, right? Should we add K up there?
Forward mean ke depan lah. Maknanya you can include K. As long as K, if you assume as 1 is okay. You can assume as 1, no problem.
Okay.
The asymptote point, sigma A, and the asymptote angle. This one is based on the formula. Okay. So sigma A using the formula. So you get sigma A minus 2.5. Okay. And the angle of asymptote using the formula. Number of poles minus number of zeros. (270°). Angle of departure or arrival. So the question asks angle of departure or arrival. So we have complex conjugate poles. Definitely is a angle of departure. Okay. So just plot it. Okay. So theta departure 1, angle of zeros, angle of poles plus 180°. So theta departure 1 is what? 108.4°.